This is video on problems on kinematics of rigid body, and we are going to do some miscellaneous problems in this video. Now the first problem which we have chosen has two links OA and AB, and where for link OA point O is hinged and for link AB B is constrained to move along that slot. So what is given is velocity of B is 2.5 meter per second at 30 degree with horizontal, and we are required to find angular velocity of OA. Now if you look at link OA, you can see that the instantaneous center is at O because it is a point of zero velocity because it is hinged. So therefore velocity of A will be perpendicular to OA as shown by the blue arrow, and B's velocity is already known. So with the result, what happens on the link AB, we have known velocity direction for point A and point B, and therefore by drawing perpendicular to these two velocities, we can locate point I, which is instantaneous center for AB. Once you have that, uh, and once we settle geometry through this sine rule, that is IA upon sine 30 is 0.4 upon sine 60 is IB upon sine 90, we write for link AB, VB as distance IB into omega AB. VB is known, IB you can get from the geometry, from the sine rule, and you can work out omega AB as 5.41. Then we write for link AB only VA. Now VA is distance IA into omega AB. Omega AB has been worked out. IA can be seen from the sine rule, and therefore you get VA as 1.25. And knowing VA, we go to link OA, in which we can write VA is equal to distance OA, because now the instantaneous center is at O. So distance OA into omega OA, VA is known, OA is given 0.2. So you can find angular velocity of omega OA as 6.25 radians per second. Next problem is three-link problem. Now, if you remember the previous videos, first task of finding velocity center in this is very simple. For AB it is A, CD it is D, and for BC is where the two end links meet. And what is given is angular velocity of AB as 15 radians per second, and what is asked is angular velocity of link CD. So we first locate this instantaneous center of BC, which is at I. We settle the geometry, we write the sine rule, and then for link AB, we write VB as AB into omega AB, because for AB, A is instantaneous center, so we take AB distance, we get VB. Now for link BC, we write, because B is also on BC, so we write VB as IB into omega BC. With known VB, we can find omega BC. And then for the same link, we write VC as IC, distance IC into omega BC. IC calculated by geometry, and omega BC known, so we work out VC. And once we work out VC, we go to link CD. Look at VC. VC and instantaneous center is D, so VC is CD into omega CD. And CD can be worked out from geometry is 0.26, and therefore we work out omega CD, because VC is already worked out as 0.85, so omega CD you get 2.25 radians per second. Next, see, this is also a two-link problem, but you see, you can say one link is or one member is a cylinder. So the system is that point B is going up, there is some kind of roller going up the wall. Diameter of the cylinder is 0.6, and we are required to find angular velocity of cylinder. And say this link is hinged to cylinder at A, and cylinder is supposed to be rolling without slipping. So what we can do is, you see, because of the cylinder, because it's a cylinder, it touches ground. For cylinder, the instantaneous center is at the bottom, and therefore VA is tangential to the circle, we draw perpendicular, and VB we draw perpendicular, we get instantaneous center I. Then for IAB triangle we write sine rule, and for link AB we write VB as IB into omega AB, where VB is known, IB is geometry, so omega AB can be found. Crop that, VA we can write as IA omega AB, I is from geometry, omega AB you can substitute to get VA. And once we get VA, we can write VA as D into omega C, where omega C is the angular velocity of the cylinder which we want, and which can work out to 3.175 radians per second. Now this case is little different in the sense you have cylinder uh, and you see the top two plates are moving as shown. Like top plate A is moving as 5 meter per second towards right, and bottom plate B is moving at 3.3 meters per second towards left. We want to locate the position of instantaneous center. Now you see, all I know now is direction of velocity at A where the cylinder touches the upper plate, and direction of velocity of B where the cylinder touches the lower plate. So instantaneous center has to lie on the perpendicular line to this velocity. Let's say it lies at I, and the logic is you see the way it has to lie between A and B, because if it lies below, then both plates have to move in the same direction. So since both plates are moving in opposite direction and cylinder has to rotate clockwise, so therefore instantaneous center has to be somewhere on the line AB within the cylinder. Once we agree to this, we write V equal to R omega. That is, suppose it is at x distance from A, then we write VA as x into omega, if omega is angular velocity of cylinder, and we get omega in terms of x. Then we write VB. Total distance is 16 centimeters, so 0.16 minus x into omega, and VB is given as 3. So we substitute there, and from these two we are able to find x, which is 0.1. So this is the case when two velocities whose direction are known are parallel to each other. Now in the next problem what we have done is we have said that both the plates are moving in the same direction. In this case, instantaneous center will be outside, and our job is to locate that instantaneous center. We write very similar equations. VB is equal to x omega. So we write omega, we write VA is equal to 0.16 plus x into omega this time. We substitute for VA, we solve for x, and x we get as 0.24 as shown in the figure. So this is again some typical problem. Okay, I think all videos together should be sufficient for at least the Bombay University requirements. Thank you.